Hello everyone, welcome back. In this video, I will be covering section 310, linear approximations and differentials. So we use the tangent line at a f of a as an approximation to the curve y equal to f of x when x is near a. Because the tangent line touches the curve, and this is the tangent line, this is the curve, and this is the tangent line. As the tangent line touches the curve at a f of a, then you can actually take the values of the function in the neighborhood of a, and instead of taking the values on the curve, you can actually take them on the line, because getting the tangent line, which is only linear, is much easier compared to finding the values of the function on the curve. The curve equation may be more complicated than the linear one. So the tangent line equation is given by y equal to, the tangent line at a f of a is given by y equal to f of a plus f prime a x minus a. So if you know that if x1, y1 is a point on the graph, then y minus y1 equal to m times x minus 1 is the equation of a line passing through x1, y1. So in this case, we have the point through which it passes is a comma f of a. So you'll be changing x to a, x1 to a, y1 to f of a. So this becomes y minus f of a, then m times x minus a. But what is m though? M is, after all, the derivative at a. Slope is nothing but the derivative. We have seen that many times now. So y minus f of a equal to f prime a times x minus a. So if you move the f of a to the other side, it becomes y equal to f of a plus f prime a times x minus a. So the equation of the tangent line at a f of a can be written as y equal to f of a plus f prime a times x minus a. And the approximation, f of x is approximately equal to the value of the function on the tangent line, which is, so f of x is approximately equal to the value of the function on the tangent line. So instead of taking the functional values on the curve, and you are taking the values on the tangent line, because tangent line being linear, it is easy to get the values on the tangent line. But it only works when x is very close to a, which means that if you find out the tangent line at a, then the values that you want to find out, the x values, the f of x values that you want to find out should be such that x is close to a. Is called, this one, f of x is approximately equal to f of a plus f prime a times x minus a, is called the linear approximation or tangent line approximation of f at a. The linear function whose graph is the tangent line, that is L of x, which is equal to f of a plus f prime a times x minus a, which you see here, which is the tangent line, is called the linearization of f at a. So f of x is approximately equal to L of x, which is the tangent line. So this is the idea behind linearization. So let's try a problem based on this linearization. Find the linearization of the function f of x equal to square root of x plus 3 at a equal to 1, and use it to approximate the numbers square root of 3.98 and square root of 4.05 Are these approximations overestimates or underestimate? So let's start with the linearization of f of x. So find the linearization of f of x is the first part of the question. So linearization of f of x by what we have seen earlier, which is the linearization. This is equal to f of a plus f prime a times x minus a. What is a in this problem? A equal to 1. There's a equal to 1. So let's try f of x, that is given to be square root of x plus 3. So f prime x, which is the derivative, 1 over 2 square root of x plus 3 times derivative of x plus 3, which is 1. That is 1 over 2 square root of x plus 3, the derivative. Then we want to evaluate that at the point A. So f prime at 1, at a equal to 1, is 1 over 2 square root of 1 plus 3, substituting. So that will be equal to 1 over 2 times square root of 4. So it will be 1 over 2 times 2, that is 4. So linearization L of x. Then we also need to find out f of a. F of a is f of 1. F of x is square root of x plus 3. So it is square root of x, so 1 plus 3. Pretty much we are plugging in x equal to 1. So that will be equal to square root of 4, that is 2. So we got f of 1, that is f of 1 plus f prime 1 times x minus 1. So f of 1 is 2, f prime 1 is 1 over 4 times x minus 1. So if you distribute, that will be 1 over x, and then you get 2 minus 1/4. That will be 1/4 of x minus 8 minus 1, so 7 over 4. So linear approximation at the point A, linearization at the point A equal to 1 on the graph is given by L of x. So this answers the first part. The second part of the question is, now use it to approximate the numbers square root of 3.98. So if you consider square root of x plus 3 as square root of 3.98, then it can be written as square root of 0.98 plus 3. So your x value becomes 0.98, which is definitely close to 1. So we can use this linear approximation or the value on the tangent line to approximate square root of 3.98. So we can write, we know that f of x, we also know f of x is approximately equal to the L of x near a equal to 1. So what is f of x? Square root of x plus 3. What is L of x? 1/4 of x plus 7 over 4. Near 1. So we can find out square root of 3.98. As we said, can be approximated by, here we are going to use this x 0.98 to approximate. So this is approximately equal to 1/4 of x, which is 0.98 plus 7 over 4. So if you use your calculator for this computation, this will be 7 over 4 plus 0.98 over 4, which will turn out to be 1.995. So square root of 3.98 is approximately equal to 1.995, which is expected because you know that square root of 4 equal to 2. So square root of 3.98 should be close to 2. So it should be 1.995. This answers first part. Then the other one, which is the second, square root of 4.05. So square root of x plus 3 equal to square root of 4.05, which can be written as 1.05 plus 3. So you want to write this in the form of x plus 3. So your x becomes x becomes 1.05. So the value square root of 4.05 is approximately equal to 1/4. We are approximating it by the value on the tangent line. This value x would be 1.05 now. We are using this relation here, plus 7/4. So this x is 1.05. So if you compute this in your calculator, it will be 2.0125. So what we notice is this value is slightly smaller than square root of 4. This one is slightly larger than square root of 4. So that's why we get a value slightly more than 2 here. So that answers the second part of the question. Now, the problem is also asking us to graphically show it. Are these approximations overestimates or underestimates? So if you notice, the square root of x plus 3 graph is square root of x plus 3 graph is square root of x shifted left by 3 units. So use the transformation of graphs. So this will have -3 as a starting point and it goes to the right. So if you draw a tangent line at the point 1, 2, because the point A equal to 1, when A equal to 1, f of A would be f of 1. F of 1 is square root of 1 plus 3, which is 2. So the y coordinate is 2. So the y coordinate is 2 here. The tangent line is above the graph. The tangent line is above square root of x plus 3. So what you're getting is, so instead of getting the values on the blue graph, you're getting the values on the red line. So at the red line is above the graph at 1, 2. So the estimates that you're getting are only overestimates. A slightly overestimate. So if you want to give a reason, say that because the tangent lies above the curve. What is a differential? If y equal to f of x, where f is a differentiable function, then the differential dx is an independent variable. That is, dx can be given the value of any number. The differential dy is often defined in terms of dx by the equation dy equal to f prime x dx. So you know that y equal to f of x. Then what is dy by dx? It is a derivative of x. So if you move the dx to the other side, you get f prime x dx. So that is what the differential is. So dy is dependent variable. So dy is dependent, dx is independent. It depends on the values of x and d of x. If dx is given specific value and x is taken to be some specific number in the domain of f, then the numerical value of dy is determined. The geometric meaning of differentials is shown in this figure below. Let P x f of x and Q x plus delta x f of x plus delta x be points on the graph of f, and let dx be equal to delta x. You're taking 2 points P, and another point Q. So P has coordinates, let's say x, f of x. And then you're moving on the right side through a distance of delta x. So the point Q has coordinates. What are the coordinates? X increments by delta x, and the y coordinate is x plus delta x. That is the coordinates of Q. These are the coordinates of Q. The slope of the tangent line. So what is this delta y then? What is delta y? So if you take rise over run on the graph, so this distance is delta y and this distance is delta x. So the distance, now you're moving to the right by delta x units and you reach the point S, and then you move upward. That is it, in order to get the y coordinate of the point Q. So delta y is raise of the curve above the point P. Delta y represents the amount that the curve rises or falls when x changes to an amount dx. We are assuming delta x and dx is the same. But what is this dy, the differential dy? Dy is the distance, the difference between S and R, or the rise of the tangent line from P. So delta y is the rise of the curve above or below P, and dy is the rise of the tangent above the point P. Okay, so there is a minor difference between delta y and delta dy and delta y. Delta y as shown in the figure, it is from the distance from R to S. What is delta y? The distance from Q to S. Okay, let's try this example. Compare the values of delta y and dy if y equal to x cubed plus x squared minus 2x plus 1, and x changes A from 2 to 2.05 and B from 2 to 2.01. Both are of same kind, only the values in the first part is 2 to 2.05. In the second part, it's 2 to 2.01. The method is the same. So we are comparing the values delta y to dy. So the idea is that we want to make delta y and dy to be almost equal. That's why it's called, the word is used as differential. So the reason, as a tangent is after all touching the curve, it becomes sometimes very difficult to get the values of the function on the curve. So we are finding the values on the tangent line. So we want to make that delta y, which is the actual rise of the curve above the point, and we are approximating by dy, which is a differential. Okay? So the differential dy is the rise of the tangent from the point P. So compare delta y and dy in this problem. So let's start with delta y. What is delta y in the problem? By definition, it is f of x plus delta x minus f of x. So it is f of 2.05. So this is the increment x plus delta x. This is the initial value x. So 2.05 minus f of 2. So what is f of x? That is given to be x cubed plus x square minus 2x plus 1. So what is f at 2.05? You substitute 2.05 the whole cube plus 2.05 the whole square minus 2 times 2.05 plus 1. If you are using the calculator, you can compute this manually, but if you remember chapter 2 technique that I taught you in the graphing calculator, you can also use the graphing calculator in y equal to, you plug in the function x cube plus x square minus 2x plus 1. This is graphing calculator technique. Then you go to the home screen where you do addition and subtraction. In the home screen, you actually use the VAR yes feature. Then you go to YVAR feature. Then you pick Y1. This will come up on the home screen, and use the parentheses and substitute 2.05 or whatever number you want to input. So same way you want to do y1 of 2 as well, because we want to find out. So in your calculator, it will look like y1 2.05 minus y1 at 2. y1 or 2 can be easily evaluated even by direct plugging in here, but 2.05 is not an easy number, so you can actually use the calculator. So it is up to you whether you want to use the calculator or not. It's fine. You can also do this manually. So I'm going to bring that up in my calculator. So I'm going to input this function into my graphing calculator. So you have a similar model. Actually, any calculator, the TI 83, 84, 84 plus, the allowed models will have this feature. In this device, I cannot bring in 83 or 84 plus calculator. So I'm using a calculator that is available in the app. So that's the one I'm showing here. So first what I did was to input this function x cubed plus x square minus 2x plus 1 by clicking y equal to and bringing in that in y1. Then I went to second and quit, and then went to the home screen, and then used the feature VAR, then YVAR, and then bring in that one. And then I input 2.5, and then go again, and then minus VAR, YVAR, and bring in that function y1, and then input 2, hit enter. So y1 of 2.5 minus y1 of 2, I should get 0.717625. So that's what I should be getting. So that shows in the previous line. So it is y1. So let's check the equation, x cubed plus x squared minus 2x plus 1. Then I'm going to the home screen. Then I'm bringing in this function. Then it is 2.5 minus, then again VAR, YVAR, Y1. Then I plug in 2.05 here. So I made a mistake there. So YVAR, Y1. Then you need to put 2.05 in the parentheses minus VAR, YVAR, Y1, then parenthesis 2, complete the parenthesis, hit enter. This is 0.717625. That is the value of delta y. So that is the one I'm going to input into the. So delta y that I computed from the calculator is 0.7172625. Right, so this is one part. Now you have to do dy. Dy by definition is f prime x dx. This is a differential. So we said that dy is f prime x dx. So what is f of x? F of x is x cube plus x square minus 2x plus 1. What do we anticipate? We want the delta y and dy to be almost equal, because this is hard to get, but dy is easy to get. So what is f prime x? F prime x is derivative of this 3x squared plus 2x minus 2. Now we want to do dy, which is equal to f prime x, which is 3x squared plus 2x minus 2 times dx. We want to calculate that at the point, at the point where x equal to 2. So at x equal to 2, so this becomes dy becomes 3 times 2 square plus 2 times 2 minus 2. And dx and delta x are the same. Dx and delta x are the same. Delta x equal to dx, which is the difference between the two, 2.05 minus 2, which is 0.05. So we know that delta x and dx are the same. So that's what we see even here. So if we use that dx, which is 0.05, so you have substituted that. If you compute this in your calculator, this value, so it is 4 times 3, that will be a 12 plus 4 minus 2 times 0.05. This will be 16 minus 2. So if you simplify this, this will turn out to be 0.7. So what we notice is that dy equal to 0.7 and delta y equal to 0.717625. This is the actual, and this is the estimate that we get through the tangent line. The estimate we get through the tangent line. So see how close these values are. That is the whole point of this. So through the values on the tangent line, we are getting a pretty good approximation to the actual estimate. So as a second part, 2 to 2.01 is exactly similar. I let you try that one on your own. So we have two answers, delta y and dy for the first part. The radius of a sphere, we'll see an application problem here. The radius of a sphere was measured and found to be 21 centimeter with a possible error in measurement of at most 0.05 centimeter. What is the maximum error in using this value of the radius to compute the volume of the sphere? All right, so the radius of the sphere, so we are talking of a sphere, the shape is sphere, and we know that we are also talking of the volume of the sphere. So the question is that the radius is found to be 21 centimeters. So R equal to 21 centimeter. With a possible error in measurement of at most 0.05 centimeter. So what this tells is that error, which is dr, error in the radius is 0.05 centimeter. That is what this statement tells us. What is the maximum error in using this value of the radius to compute the volume of the sphere? So let's start with the volume of the sphere. Which is 4 by 3 pi r cube. Okay. We can actually assume that dr and delta r are the same here. So if the measure is, if the error in the measurement of value of r is denoted by dr, the error in the measurement of r is denoted by dr, then it would be same as delta r. The corresponding error in V in the volume is delta V, which can be approximated by the differential dV, correct? This is the way we approximate. We take dy in place of delta y. We can take dv in the place of delta v. So delta v is actual, dv is the differential. So now we are going to use dv in the formula. We are going to use dv, which is 4 by 3 pi, then derivative of r cube, which is 3r square dr. So this 3 and 3 cancel out, which becomes 4 pi r square dr. dr is given in the problem, and also r is given in the problem. So we know these values. R is 21 centimeter and dr is 0.05 centimeter. So it is 4 pi times r, which is 21 square, dr, which is 0.05. So it is 21 is centimeter square, then radius square, that will be 21 centimeter times 21 centimeter. So you have centimeter square from here, then 0.05 in another centimeter. So volume will be centimeter cube in terms of measurement. So when you compute these values in your calculator, you can use a calculator for this one. This will be approximately 277 centimeter cube. So the error in the volume, the maximum error in the volume would be 277 centimeter cube due to the error in the measurement of the radius. So the maximum error in the volume is approximately 277 centimeter cube. Let's do a couple of problems from the additional suggested problems. So it's a good practice to try all of them. Let's try number 3. F of x equal to cube root of x at a equal to 8. What is asked is the linearization L of x of the function at a. So let's write down what linearization is. This is problem number 3. This is also on the practice exam. So this is given to be f of x equal to cube root of x at a equal to 8. So what is linearization by definition? Linearization is f of a plus f prime a times x minus a. This is what linearization is. So here a equal to 8. So it is f of 8 plus f prime 8 times x minus 8. F prime 8 at times x minus 8. So what is f of x? Equal to cube root of x. So it is x to the power 1/3. What is f of 8? Cube root of 8, which is equal to 2. What is f prime x? Which is 1/3. X to the power 1/3 minus 1. So it's 1/3 x to the power negative 2/3. If we do f prime of 8 there, which is 1/3 8 to the power negative 2/3. So f prime 8 is 1/3 8 to the power negative 2/3. If I do a bit of algebra or use your calculator, you can bring it down and then you write that as 8 to the power 1/3 the whole square, which is cube root of 8, which is 2. 2 square, that will be a 4. So 4 times 3, that will be 12. So our L of x now becomes, if I substitute these values here, namely f8 and f prime 8, so it will become f8, which is 2, plus f prime 8, which is 1/12, times x minus 8. So it is 2 plus 1/12 of x minus 8/12. It is 2 plus 1/12 x minus, we can even consider 12 as our LCD. So if we do LCD here, it will be 1/12x plus 2 minus 8/12. If you can reduce that, so that will be 2/3. So that will be 1/12x plus 6 minus 2, which will be 4/3. So the linearization in this case turns out to be 1/12x plus 4/3. So what it means is, if you want to find out the value of the function in the neighborhood of 8, say you want to find out the value f of 8.1, let's say. So it is a value very close to 8. We are looking at this number very close to 8. So it can be approximated by the value of the tangent line. So I can just plug in x equal to 8.1 over here, then find out the value. So in the neighborhood of 8, f of x can be approximated by L of x. That's the idea of this problem. Let's try this problem here. Find the differential of each function. This is also on the practice exam, number 13. Y equal to 1 plus 2u over 1 plus 3u. The question is differential. The question is asking you to find out dy. So dy is this derivative 1 plus tu over 1 plus 3u, the derivative of that times du, because y is a function of u. So y being a function of u, what you're doing is dy is f prime u du. So let's get back to this step a little later. Now let's compute what this 1 plus 2u over 1 plus 3u derivative of that is. So it is something like uppercase u, uppercase v prime, quotient rule. So it is the so I'm going to keep the uppercase u as 1 plus 2u. Then uppercase u prime, the numerator derivative is 2. Then uppercase V is the denominator, 1 plus 3u. Its derivative is just 3. So when I apply the quotient rule, 1 plus 2u over 1 plus 3u prime is going to be denominator times derivative of numerator minus numerator times derivative of denominator over denominator square. I'm using uppercase U and V because lowercase u is used in the problem. So V first, which is 1 plus 3u multiplied by u prime, which is 2, minus uppercase U, which is 1 plus 2u, V prime, which is 3, divided by denominator square, which is 1 plus 3u, the whole square. So if I distribute, I'll get 2 plus 6u minus 3 minus 6u divided by 1 plus 3u, the whole square. This 6u cancel out. So going back to, so I already got the 1 plus 2u over 1 plus 3u derivative. So that will be equal to negative 1 over 1 plus 3u, the whole square. So if we call it step 2, we will substitute 2 into 1 in 1. We get dy equal to the derivative, which we got here as negative 1 over 1 plus 3u, the whole square, followed by what? Followed by du. That is the differential. Let's try one word problem, which is on the practice exam, number 36. Use differentials to estimate the amount of paint needed to apply a coat of paint 0.05 centimeter thick to a hemispherical dome with the diameter 50 meters. So we are looking at spherical dome. It is about paint, so we are looking at the volume. So, and it says it's a coat is a paint 0.05 centimeter thickness. That it kind of suggests that it is dr. So we are going to apply the dr, that is the radius, change in the radius. And it is hemispherical. The diameter is 50 meters. So 2 times the radius is 50 meters. So one little change you may want to note, that this is in centimeter, this is in meters. So you may want to bring everything to one unit. We will bring everything to meters here. So I have copied this problem here. So let's start off with the hemispherical dome and the volume of it. So volume of a sphere is 4 by 3 pi r cube. So volume of a hemisphere is half of it, which is 2/3 pi r cube. So if you do dv, which is 2/3 of pi, which is a constant, outer derivative, derivative of r cube with respect to r followed by dr. So are we given all the information? This 3 and 3 cancel out. So it is 2 pi r square dr. dv is a change in volume. So it's the amount of paint that we need. So in this case, you are given 2r to be equal to 50 meters. That gives r equal to 25 meters. And to apply a coat of paint 0.05, this gives us 0.05 as our differential in r. So we'll substitute all of that over here. 2 pi 25 square times, one thing about this 0.05 centimeter, if you convert that to meter, you are going to divide by 100. So it becomes 0.0005. So that will be the dr here in terms of meters. So that is important here. We're converting centimeter to meter, because the other unit is in meters. 25, the radius is, this is in meters. So it is 0.0005. If you compute that in your calculator, it is about 5 pi by 8. So if you lose your calculator for this, it will come out to be 1.96. So we can say approximately it is 2 meter cube. So dV is approximately 2 meter cube. So we can say the estimation of amount of paint is actually 2 meter cube. Paint needed to apply a coat of 0.05 centimeter thick. So that completes this section. So there is one more short section that we will be doing. So watch my next video for section 311. Hope this video helps.